This presentation is going to be looking at steel girder bridges. And so specifically the I-95 overpass at Cottman Avenue that collapsed last summer in June due to a severe tanker truck fire. We've been doing some work for PennDOT, Pennsylvania Department of Transportation, and they've been very proactive in looking at how to protect their bridges and what they can do better. And so we're looking at some potential for passive protection in addition to trying to do the modeling to verify the mechanisms of what happened. On the outset, if you look at this this event, big large tanker truck fire, very minimal clearance right underneath the bridge, it's going to be a bad outcome. But PennDOT wanted to know could this be modeled as a scenario if they wanted to do design or evaluation elsewhere, and also if they were going to try and put mitigation, some kind of passive mitigation on this bridge or other bridges, how would it fare? What kinds of products and how much would be needed to actually achieve a suitable performance objective? So the presentation, we're going to focus on steel girder bridges under severe fire exposure. This work again has been supported by PennDOT and features a lot of SAFIR. So it's we've been we're always very appreciative of the capabilities that that SAFIR can provide us with doing these analyses, and we've been coupling that with some of our own fire modeling capabilities and calculations, and looking in particular at potential mitigation for how we can make it better under these kinds of fires. So really quickly, fires for bridges has become an increasing area of concern. The U.S. Federal Highway Administration has been starting to fund work in this area. There's not a whole lot of guidance currently out there in terms of the AASHTO or the state DOTs, but fire, even though it's a small sliver in red right there, it makes bridges fail on an annualized basis that's comparable to construction defects and earthquakes. And so we do a lot more in terms of inspection and design for both of those. And that's a relatively small percentage, but it's a high consequence event. Hydraulic, collision, overload, those are obviously much bigger, but fire is it's comparable to some of the other ones that we spend a lot more time on. And so entities like PennDOT have become a lot more concerned as it's been happening more and more. So the I-95 Cottman Avenue in Philadelphia, so the bridge is just over 100 feet in span. The clearance is just over 14.5 feet, so very relatively low clearance bridge. It was only 12 years old at the time of the event last year. It was subjected to a tanker truck fire, the truck was carrying 8,500 gallons of gasoline that was estimated. The bridge failed in just a little over 10 minutes due to the extreme exposure, and then the fire continued for about an hour before they got it under control. So we have a little image here showing approximately where the truck crashed. The truck was exiting I-95 and descending down an off-ramp, and that off-ramp then curves and goes underneath the overpass to right here, where the driver lost control and it struck the abutment wall. The truck overturned, and due to the crash, right underneath the northbound span, that's where the fire ignited. And then the southbound span was adjacent to this. Northbound collapsed. Southbound did not, as you can see here. But southbound was sagging and damaged enough where they ended up demolishing both spans anyway. And so the estimated heat release rate for this kind of truck fire would be approximately 300 megawatts. That's a number that's been established by the National Fire Protection Association, and it's available in their guidance. And it's a relatively typical steel girder highway overpass. So this is not a design that was, had a lot of uniqueness or uncommon pieces to it. This was a very, straightforward design in the PennDOT inventory. And they were, kind enough to provide us with all the drawings so we could do all the appropriate modeling of the sections and the slab and everything else. And so where do you get started with these bridge fire projects? Chapter 6 in NFPA 502 has some guidance, but the really big thing right away that you see there is that it really applies to bridges with spans over 300 feet to do all those things: support firefighter accessibility, minimize economic impact, mitigate structural damage. So something like, a cable stay bridge is what you see here with the Cuomo Bridge. Those types of more signature structures fall into that category, but the provisions in NFPA 502 are not necessarily required for spans that are less than that. And most of the bridges that have been adversely impacted that we showed earlier mostly just typical overpasses in high traffic areas with high levels of vulnerability. So the engineering analysis, if you were to apply the NFPA 502 requirements, an engineering analysis is needed to determine if the bridge could withstand a fire without collapsing. And it gives you some guidance depending on what the bridge is going over for what kind of hazard you should use. But the engineering analysis is not specified. And so we've been using SAFIR in combination with our fire modeling tools to do this type of work for PennDOT. And so, using performance-based structural fire engineering, 3 steps: fire model, heat transfer model, structural model. And again, with SAFIR being featured prominently in the heat transfer and structural models, we've been trying to synthesize these approaches that take reasonable representations of fire, of bringing the heat to the structure, and then seeing what the structural response is, so that PennDOT can begin to make decisions about what kind of thermal and structural vulnerability do we have, how do we select products to actually protect these assets, and what is the potential outcome. Even if we apply passive protection, what should we be expecting from a damage perspective? And so the approach that we've been applying is somewhat of a, I don't know if you would necessarily call it intermediate, but that's what PennDOT has liked that term. We're not using the highest order of computational approaches. We're also not using things that are single calculation spreadsheets. It's trying to basically go in the middle between certain levels of complexity to determine the fire characteristics, calculate the heat transfer from the fire to the structural targets, calculate the temperature increase of those elements, and then calculate material and mechanical response of the structure. So we'll go through each of those steps as it applies to the I-95. The fire characteristics, establishing, yes, this was a tanker truck. We have an established heat release rate that's based on NFPA 502. But then having to also look at what is the footprint of the fire, how long does it take to burn away the fuel, how much of that 8,500 gallons would be available. You are going to have some runoff, some absorption, what would be a reasonable approximation that helps determine the length of time. And so you get a heat release rate time history from all of that, and also fire geometry, particularly the flame height and just the breadth of the flame object of the fire. So for a hydrocarbon pool fire, there are established equations for determining flame heights and also the heat release rates based on the fuel. Solid fuel fires, we've done a few of those using inventory methods for PennDOT as well. And that's been in response to some other events for bridges collapsed due to burning storage materials underneath the bridge. And also then vehicular fires, which you can, instead of doing hydrocarbon pool calculation, you can then just revert to the heat release rate that's in the tables from NFPA, and then use those as the basis for calculating flame heights based on what kind of footprint you have. So with those things in mind, to establish how long the fire would burn, how high the flames would go, and what the overall size, the breadth of exposure would be, we then use a model that we've coined the MDSF, or the Modified Discretized Solid Flame. So we've been progressing with this model through several different iterations, and this is really the second edition of this model. We've used it on the MacArthur Maze fire, which happened, more than 15 years ago in Oakland, California. We've used this now, also looking at the Harrisburg fire incident from 2013, and then also this one, and also the I-85 in Atlanta from several years ago as well. And so it basically takes the solid flame, the fire object, and then discretizes its surfaces into tiles, and you can begin to divide them up into visible flame and then also smoke obscured elements. And so you have the flames underneath, and then also a luminous zone, which is it can fully have visibility of the structural objects. And then the smoke cone, which sits on top, and that helps shield some of the emissivity coming off of the flame. And then you can calculate the total heat flux, so the contribution of all tiles that can see a target, that on any object which is adjacent to the fire, if the bridge ends up confining the fire and kind of smashing its top, you can then begin to spread it out. You have the smoke cone with the same volume that begins to then go in a different direction. You change the shape and smash it into the underside of the bridge deck. You have flame inundation, and so you can calculate your heat flux fields using this confined portion of the model. So we do both when we look at particular types of exposure. And if we have a fire, again, this was not the case for I-95, but if we have one which is just adjacent to the bridge, the fire goes up, you have tapering down of emissive power as you go higher in the smoke cone. We validated this model against numerous experiments, especially for hydrocarbon pool fires, and then also using FDS models for further verification. And so you get a spatial distribution of the heat flux exposure and the time history. So for how long this would take to burn out. So if you switch over to confined fires, again, that the smoke and the flames smashes into the underside, spreads out, and then you see a much more severe distribution of peak heat fluxes, depending on how close you are. So depending on your proximity to the fire and the clearance. So for I-95, the truck, hit the abutment wall on the north side of that off ramp underneath the northbound span, and then caught fire, heat release rate of 300 megawatts. So this fire, the way the MDSF is working, it's severely smashed underneath the fire because that is going to have a high flame height, approximately a 50-foot length. We use an elliptical shape rather than circular, and we have some strategies for how that then creates the cone shapes. We can kind of mold it to get more of a lengthwise fire. And so looking at the isometric view for how this tapers around with the smoke, those edges that are smashed that kind of go into the abutment wall or outside the bridge. I mean, it's assuming that those are going to be escaping going vertically. So this, the entire shape is smashed, if any of it is smashed. And then looking at the heat flux distribution that we end up getting underneath the fire, we can see the highest levels of intensity. The engulfed values get up to about 170 kilowatts per meter squared. That's that's consistent with the high end of like the ASTM 29 and also experiments. And then the time history going just a little bit past an hour for how it burns out. Taking those heat fluxes, we can then apply it to our cross sections in SAFIR to figure out how much this heats up. So we can then come up with the target temperature increases for these fiber sections, depending on their boundary conditions and their exposures, and get their time histories. Northbound, they were inundated, so we had all sides on the underside of the structure that were heated, and we did it in length increments, so about 3-foot increments going across the bridge. So we do get the differential heating across the length, and then southbound, 2 sides heated because it was getting side swiped. Again, it was discretized along the length to see what the residual damage was there. So calculating the structural response, if we have the boundary conditions and the loading, which again, based on information we got from PennDOT, we can estimate what the base loading was. We typically are just using dead load plus of 30% of just the uniform lane live loads. Very low live loads. It's not a whole lot driving across the bridge in these situations. And so we've done 1.1 times dead load. So more of a minimal amount of loading that doesn't consider a whole lot of live loading. And then taking our cross sections as thermal input and putting it into the models. Again, these boundary conditions for how the ends are restrained. This was done in consultation with PennDOT and their drawings. And we can get then deflection time histories and eventual damage or estimates of collapse. So the I-95 overpass, each of these girders here, they're all pictured together from their results. And this is at the same time. This is at 690 seconds when the first girder collapses. They're analyzed individually. So the decision was made, we had proposed to PennDOT that we could do something where we had shell connectivity between the girders. Some preliminary calculations that we were performing indicated that it really wasn't going to change the results that much in their favor. And so we did them as individual analyses. And at 11.5 minutes, the first girder collapses. Very soon thereafter, you get another 4 that collapse. And so based on where the fire was and which girders go first, and then what the shape was in terms of eventual failure, we had a lot of consistency in terms of what we were predicting. And then also, not only just with northbound, but also with southbound, where for southbound, it should not have collapsed. And so if we look at the worst girder on southbound, we were sagging a lot. We got a decent amount of deflection. It was also evident in cell phone videos. There was actually one car that drove across southbound during the fire event, and you can see the car basically go down and then up as their cell phone video was rolling. And so we end up with a level of residual damage. And we've come up with a classification system for PennDOT that they've liked, which has taken some of these serviceability limits in AASHTO and then scaled with the residual effects that you get post-fire, going from superficial, where it's very small, you can potentially reuse the bridge, moderate, a little larger amount, requiring more repair, possible replacement, heavy post-fire replacement is most likely going to be required. Hazardous, the probability of collapse is increasing, replacement's going to be definitely required, and then collapse. You basically get to runaway deflections sometime during the analysis, which is what we saw with northbound. And so PennDOT was satisfied with the way these calculations were predicting what happened in the event and the collapse that was observed. But then they were interested in how would this be able to be improved? What kind of protection could we provide for it passively, and have to be corrosion resistant, weather resistant, relatively lightweight, cost effective, can't inhibit routine inspection. And so these are things that they're beginning to explore. This is going to be a subsequent project. And so obviously things like SFRM and gypsum boards, in this environment aren't going to work. But the good thing about these materials, we have a lot of data in terms of how to model them in SAFIR. Intumescence, this is more of an ideal product. It's a little more costly. And also the thermal material properties are still being developed in terms of, what kind of performance would you expect? So what we end up doing is performing somewhat of a virtual fire test for them, and using SFRM as a stand-in. So if we can develop what kind of hourly rating would be needed per the ASTM E1529 or even the E119 curve. E119 is for buildings, but a lot of products are rated using that curve. How can we then come up with thermal performance on this bridge, structural performance, establish relative quantities of fire protection to meet an hourly rating with a virtual test, and then compare that to what the actual performance of the bridge was. And so something that they've been really interested in is taking these hourly rating metrics, so mid-span deflections, these are all out of the 119 criteria, critical temperatures of the steel beam, thermal transmission through the slabs, what these metrics are, in a testing environment, but then how do we make them talk to a performance-based structural fire design? So can we use calculations to do the virtual standard fire test to figure out what hourly ratings of a product correspond to each severity, and then from a performance basis, go back to the actual structure and the actual fires with those rated protection levels and figure out what is the expected measure of performance so that they can go buy a product. So that's one of the things they're very concerned about, is how do we actually select what is going to help us and what can we expect it to do. So the modeling approach that we did was using SFRM as a stand-in. So we have those material properties. We used some published results that were produced, led by Nagar Khorasani at University of Buffalo, and using their mean curves for thermal conductivity, specific heat density, plug those in, do virtual standard fire tests for the cross sections we have. So what hourly ratings could we derive with that for certain levels of protection? Take those levels of protection, subject them to the 2023 event, and then look at performance versus hourly rating. What would you get? And so with that, looking at a couple of our cross sections here in SAFIR, this is for the hydrocarbon exposure 1529. Initially using thermal, so maximum and average, and maximum temperature is for these types of cross sections is typically governing. So determining a thermally rated hourly selection. So hydrocarbon and building fire, because E119, again, it's how a lot of the vendors are rating their products. We're doing both and looking at for hourly rating versus SFRM thickness, what would you get? Then also going back and doing the virtual standard fire test on the structure itself to say by deflection versus the governing temperature criteria. We saw they're actually relatively consistent. So especially for these levels of loading, again, it's going to be load dependent. We've done some other work on that. So what kind of hourly rating would you get by deflection basis versus thermally? Thermally is nice because, again, it makes it more flexible. You can do it for more types of scenarios. But then taking those results, so each of those protection increments, and subjecting to the actual event, what happens? Does it collapse, heavy damage, hazardous damage, moderate? And PennDOT really is interested in getting all the way down to superficial. If they're going to put fire protection and spend the money, can we reopen the bridge? That becomes the chief question. And so we can do correlations with different rating types for stepping down for if we apply 1 hour of a rating per this curve, this is the expected measure of response that you would get in response to the actual event for the actual structure and loading. So these types of tables have proven very useful in their discussions with some of the vendors they've had thus far. But what they're interested in more is from the conclusions of this project is then using these modeling methods with intumescent products. But first, we're going to be doing some testing. So they want to explore, what kind of residual damage would be expected. Obviously, it's going to slow down the temperature growth. It's going to provide some benefit. But if they have to demolish it anyway, they had to take southbound down in addition to northbound, which totally collapsed. Both bridges were a total loss. So they want to know from a relative sense, what would actually provide tangible benefit to meet a given performance objective. And so that's going to be leading to new research that we're going to be doing in the next 2 years here at Lehigh. I know it was a lot in 20 minutes, but thank you again for your attendance today. This is a great event. I'm excited to see all the other presentations and the things being done with SAFIR around the world. And I'd be happy to answer any questions.